So now let's actually get to finite volume. So now finite volume is basically a discretization aimed towards resolving shock waves. If you have any discontinuity, use finite volume. Okay, and where do we start? Let's say if I ask you, please derive me a discretization method that can solve differential equations like that with shock waves, where would you start? Yes, we have three forms, and only the integral form makes sense, right? For equations with shocks. So of course we have to start with the integral form. Unlike finite difference, which started, I mean, you can actually apply finite difference either to the conservative or the primitive form, right? But both starts with a formulation that doesn't make sense when the derivative doesn't exist. So we'll have to start with the integral form. So it's always start with ddt of ab of w dx plus f of w ab equal to 0. So that's always where we start. Now, in finite volume, we have a similar type of grid, right? We have 0, delta x, 2 delta x, like n delta x. But what we do to the solution, what we do on the grid is completely different. So yeah, so we are having a class until 11. Yeah. Yeah, so remember, if we do finite difference on the demo, if we draw a function, right? So we are only, the finite difference is storing the solution, is storing the function on the grid points, right? But if you do finite volume, what you get is different. So let's try to draw the same function. Don't know if I can. Oh yeah, actually this actually works. Okay, so if I have the same function and I use finite volume, this is what I get. Okay, what am I getting? Can somebody tell me what I'm getting? The average of the function over the cells. And why does it help for the integral form of the differential equation? How does the average of the function relate to the integral form of the equation? Yes, the average over a volume is nothing but the integral of the volume divided by the size of the volume, right? So that's what average is about. It's just a constant multiple of the integral. So if we have the average of the function, we actually have exactly this. Right, I mean, actually we can rewrite this as ddt of delta x times the volume average, right, over a cell. So let's say this is cell 1, cell 2, cell n. So cell I is plus f of w at, let's see, I minus 1 delta x, I delta x, right? Okay, in finite volume, actually, the grid points no longer matters that much. What matters is actually the cells, right, or the volumes. And so let's actually denote, let's adopt a new notation. Let's denote I delta x instead of denoted as xi, because I delta x is actually to the right hand side of the volume I. So let's denote it as xi plus half. Okay, while xi minus half is actually I minus 1 delta x. I mean, why are we doing this? Because, I mean, this is actually convenient, saying that xi plus half is right in between the cell I and the cell I plus 1, right? While xi minus half is right in between cell I minus 1 and cell I. So that's makes it very convenient. And we are also going to see that one of the advantages of finite volume is that the algorithm is very insensitive to the distribution of the volume sizes. So if you have a non-uniform grid, my code is going to be exactly the same, right? While in finite difference, if I change the grid size, I have to do Taylor series analysis again to derive a different stencil, right? Maybe I lose all of accuracy and things like that. But in finite volume, actually, if I change my grid size, nothing changes because the integral form, actually, you can just change A and B, right? So, so it doesn't, the integral form doesn't change. Okay? So now somebody tell me what is missing. Right now I have no approximation whatsoever, right? So this is exact. This is exact. So can I plug this equation? Sorry, equal to 0. Can I plug this equation into computer and start solving it? What am I missing before I can implement this? Huh? Yes, so these values I no longer have. Like, unlike in finite difference, I have exactly the value of my function w at these grid points. Now I don't. I have no idea what the value of my w at the grid points are, right? So I lost it. I only have these averages. I don't know this value. I don't know this value. Right? I don't know this value. I have no idea knowing this value. Right? So from these two cell average, how can I predict that the on the interface between these two cells is actually W would be equal to that? So since I don't know the W at the interfaces, I also don't know the flux. Can't evaluate f of W on the interfaces. So the approximation finite difference has to make. Finite volume has to make is that how can I compute W of I plus half from neighboring cell averages, right? For example, most simple thing we can do is just take f wi plus half approximately equal to the average of wi bar and wi plus 1 bar. So that's one way of doing the approximation. But like what I'm saying is that you have to do some approximation, right? The approximation, for example, would actually work pretty well over here, right? The average of them gives the right answer. But it doesn't work very well over here, right? So the average is over here, while the two values here. So that's what finite volume is about. Basically, it's about taking the integral form and choose my integral range to be small volumes that tiles the entire domain of your solution.